My name is Erik Stuchli from the University of Bristol, and I will talk about our research which focuses on a reward-based analysis of optimality in decision-making. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Many of you here work with different models of decision-making, which attempt to describe and explain decision behavior through a set of underlying mechanisms represented by tunable parameters. An often unaddressed question is why these model parameters end up taking the values that they do. The implicit assumption of many models is that agents are trying to optimize some outcome variable, where being optimal simply means that the selected parameter values yield the best outcome out of all possible alternatives. Because many decision paradigms involve real or imaginary rewards for correct responses, the assumption often is that the decision maker's goal is to maximize gains, or optimize their reward rate. As an example, here we have a 3D graph of a hypothetical parameter space with parameters θ1, θ2, and the outcome variable reward rate. As you can see, the outcome with the highest value is generated when both parameters have the value of 0. Of course, different combinations of these parameter values will lead to outcomes closer or further away from the optimal one. For instance, point B is certainly less optimal than point A. And as such, the degree of optimality or suboptimality itself can be considered a spectrum rather than a clear-cut dichotomy. By definition, note that the outcome can only be considered optimal or suboptimal with respect to the parameters being considered, in this case θ1 and θ2. A large number of parameters could be considered when we talk about optimizing decision behavior. For now, though, let's focus on the evidence accumulation framework, which assumes that participants sample and integrate noisy evidence until it reaches a predefined level, a decision threshold, which triggers a decision. Out of all parameters in the evidence accumulation framework, decision makers have the most direct control over selecting these thresholds, essentially allowing the decision maker to set a decision policy, which dictates when a decision is made, which in turn determines the amount of reward rate the individual can obtain. So when talking about optimizing gains in decision making, it makes sense to consider threshold-related parameters, such as their height or their gradient, the rate of change over time. And indeed, that is what many optimality analyses of decision-making involve. Normative models typically compute what the optimal height of the thresholds should be in a given context. However, the information about the variable that is being optimized is often discarded, and only the parameter value itself is extracted. Statistical tests are then used to compare the thresholds adopted by decision makers against this extracted value to see whether the chosen policies are significantly suboptimal or not. This type of optimality analysis has been used to argue, for example, that individuals trade off response speed and accuracy during a decision in order to maximize the reward rate. More recently, optimization frameworks have also been used to argue for collapsing decision boundaries as the optimal policy during certain decision-making tasks, such as when easy and difficult decisions are randomly intermixed. We are going to focus here on one such analysis performed by Malhotra and colleagues, whose primary aim was to examine whether individuals use collapsing thresholds in contexts where they represent the optimal policy. Participants completed blocks of easy-only decision trials, as well as blocks where easy and difficult trials were randomly intermixed. In line with the optimality analyses mentioned before, the authors then simulated optimal decision-making agents, seen as red crosses here, to compute the optimal policy. You can see that the best strategies were to employ constant thresholds on the single difficulty easy blocks, and mildly collapsing thresholds on the mixed difficulty easy blocks, respectively. Participants' threshold gradients were then inferred and compared to these optimal agents. Surprisingly, individuals tended to systematically over-collapse their decision thresholds across experimental conditions. So collapse thresholds more than necessary on the mixed blocks, and use collapsing thresholds even on the single difficulty blocks, when the optimal policy would be to keep the boundaries constant. Now, this was a highly peculiar finding because certain studies found that individuals do not tend to use collapsing boundaries even in contexts where they represent the optimal policy. To get a more holistic understanding of why this might be, Malhotra and colleagues went beyond a simple numerical comparison of threshold gradients and computed the reward rate associated with each decision policy. So the different combinations of decision threshold intercepts, their starting heights, and different gradients, so the rate of change over time, corresponding to slightly increasing all the way to instantly collapsing here. You will notice several features of this landscape, such as that the optimal policies occur here around the gradient of 0, which is consistent with what we have seen in the previous slide in terms of the single difficulty easy blocks. You will also notice that there is an asymmetry in the drop of reward rate relative to the optimal policy. So employing increasingly more negative gradients leads to a gradual drop in reward rate, whereas employing thresholds with an increasing gradient would lead to a very rapid drop of reward rate. And these are the participant level policies superimposed over the landscape. As you can see, only few individuals actually selected the most optimal policy. However, most participants did select a policy which yields near optimal levels of reward rate within this relatively large area here. And the idea is that the shape of this landscape itself is responsible for the participants' choice of overly collapsing boundaries. Consider the decision maker's perspective. They do not have prior knowledge of how exactly this reward landscape looks like and how good or bad the various policies are on the task, meaning they have to infer the information somehow. One way to do this is by exploring the landscape. So selecting an initial policy and trying a different one, generally changing direction if reward rate values drop and remaining on course when it increases. And that way, gradually, the individual will approach the optimal policy. However, note that quite a wide range of policies falls in this area over here, where the reward rate is relatively high and does not fluctuate much, whereas further exploration can result in the loss of reward rate, and particularly at policies with more positive gradients, where the decrease in reward rate is way more rapid. That could explain why participants may simply abandon further exploration and return back to the policies which they know yield a good enough reward rate. And it would also explain why some participants never get all the way to this relatively tight cluster of most optimal policies. This relates to the concept of satisficing. To paraphrase Herbert Simon, who proposed the term, it's the notion that if an agent cannot discern the optimal solution to a decision problem, the next best approach is to select a policy that will satisfy the vital needs of the agent. Among others, such an approach is particularly useful when there is uncertainty about the structure of the environment, which there is in our case, since participants do not have prior information about the reward landscape. So under this view, decision makers do not act as optimal agents, but rather satisficing agents. So, the satisficing account rests on the assumption that individuals settle for a policy which yields good enough levels of reward rate, because the costs and risks of further exploration might prove too great. That is, it is a risk avoidance strategy. This means that if the optimal policy were the same, but the negative gradient thresholds yielded lower reward, settling on the same policy would prove to be way less beneficial, and thus we would expect an agent to select a policy closer to the optimal one if they wish to obtain the same levels of reward rate. So in essence, Making the reward landscape more symmetrical around the optimal policy should push agents to adopt policies closer to the optimal one, and vice versa. To our knowledge, no one has previously examined this framework in decision-making, and so it is unknown whether or how such changes could be introduced to the reward landscape, which was the primary aim of our recent computational work. To answer this question, we developed a Monte Carlo simulation of the decision task used in Malhotra and colleagues' experiment. In these simulations, discrete evidence samples were presented sequentially, and they could either support the correct decision option with a probability p, or the incorrect option with a probability 1 minus p. We also made sure that the values of simulation parameters directly correspond to the task parameters employed in Malhotra and colleagues' experiment. And we then systematically manipulated these values to identify whether any of the parameters can produce the desired change in the reward landscape. In the end, it turned out that parameters related to incorrect responses, so monetary penalty and the additional waiting time after an incorrect decision, have the capacity to produce such change. And here you can see the landscapes generated by our Monte Carlo simulations, with parameters of the baseline condition corresponding directly to the task parameters used in Malhotra and colleagues' experiment. Relative to this condition, you can observe that both the time and monetary penalty manipulations have kept the optimal policy largely the same, while lowering the reward rate associated with non-optimal policies, particularly those with negative gradients. This pattern may be better seen in a cross-section across these landscapes, which pass through the optimal policy. First, we can see the baseline condition landscape, with the optimal policy at 0 and an asymmetry in the decrease of reward rate. And for comparison, here is a cross-section of the monetary penalty landscape. Notably, the optimal policy is still very close to 0, but we can observe a significantly steeper decrease in reward rate for thresholds with increasingly more negative gradient. So, it looks like we are able to change the symmetry of the reward landscape, which allows us to make a prediction. If individuals act as satisficing agents, they should adopt thresholds with gradients closer to 0, and the between participant variance in these gradients should be lower in the more symmetric penalty condition than in the relatively forgiving baseline condition. And lastly, here is a comparison which also includes the time penalty landscape cut. Notably, this landscape shows reward rate levels highly similar to the monetary penalty landscape, except for the very extremes here and here. So not only does this mean that we have been able to change the shape of the reward landscape in a way that allows us meaningful predictions about participant-adopted policies, but, provided that appropriate parameter values are selected, we expect that both types of penalties should affect decision behavior the same way. So, to conclude, many model-based analyses of decision-making assume that individuals aim to maximize reward by selecting optimal values of parameters, such as decision thresholds. However, when declaring an individual's performance as optimal or suboptimal, analyses should not only focus on the adopted parameter values, but also consider the actual performance or outcome those parameters yield. This was illustrated in an example with the reward rate landscape for various decision policies. It was further proposed that the non-uniform shape of this reward landscape may encourage participants to act as satisficing rather than optimizing agents. And finally, we showed that penalty-related task parameters can change the shape of this reward landscape, allowing us to make the prediction that increasing the landscape symmetry should motivate participants to adopt policies closer to the optimal one, a prediction we are currently testing in a decision experiment. I would like to thank my supervisors, Dr. Casimir Ludwig and Dr. Gaurav Malhotra, both of whom have contributed significantly to the project as presented here. And finally, thank you for your attention, and I will be happy to have further discussion on the forum.